Welcome to this video lecture series on transportation engineering. In this session, we shall discuss on the tests on soil. Now, as we know that the subgrade soil is an important part of the road pavement structure, as it provides this support to the different layers of the pavement. And the subgrade soil and the properties of the materials used in order to construct the subgrade are very important in the design of the pavement. The main function of this subgrade is to give the appropriate or adequate support to the pavement, and for the same reason the subgrade soil should have the capability to support the pavement with utmost stability under the adverse climatic and the wind loading conditions. Hence, it is very essential to evaluate the subgrade by conducting the tests either in the laboratory or on in situ test or the field tests. The tests which are used in order to evaluate the strength properties of the soil are divided into three groups. First is the shear test, second is the bearing test, and third is the penetration test. Firstly, we shall discuss on the California bearing ratio test. The California bearing ratio test is a penetration test developed by the California Division of Highways as the method of evaluating the stability of the subgrade soil and other flexible pavement materials. The test results have been correlated with the flexible pavement thickness requirements for the highways, and the CBR test may be conducted in the laboratory or in the field. The laboratory's CBR apparatus, it consists of a mold of 150 mm in diameter with the base plate and a collar, a loading frame with the cylindrical plunger of 50 mm diameter, and dial gauges for measuring the expansion on soaking and the penetration values into the soil. The penetration test, it consists of causing a cylindrical plunger of 50 mm diameter to penetrate a pavement component material at 1.25 mm per minute, and the loading values to cause 2.5 mm and 5 mm penetration into the soil are then recorded. Now, these loads, they are expressed as percentages of the standard load values as respect to deformation levels in order to obtain the CBR value. The standard load values obtained from the average of the large number of tests on the crushed stone are 1370 and 2055 kg respectively at 2.5 and 5 mm penetration. The specimen in the mold is then subjected to 4 days of soaking and the swelling, and the water absorption values are then noted. The surface weight is placed on the top of the specimen in the mold, and the assembly is placed under the plunger of the loading frame as shown in the figure. The loading values are noted corresponding to the penetration values of 0, 0.0, 0.5, 1, 1.5, 2.0, 2.5, 3, 4, 5, 7.5, 10 and 12.5 mm. Then the load penetration graph is plotted as shown in the figure. Two typical types of curves may be obtained, as you can see from the figure. The normal curve is with the convexity towards as the specimen number 1, and the load corresponding to 2.5 and 5 mm penetration values are then noted. Sometimes a curve with the initial upward concavity is obtained, indicating the necessity of the correction as for the specimen number 2. Now in this case, the corrected origin is then established by drawing a tangent AC from the steepest point A on the curve. The load values corresponding to 2.5 and 5 mm penetration values from the corrected origin C are then noted. The causes of the initial concavity of the load penetration curve calling for the correction in the origin are due to: first, the bottom surface of the plunger or the top surface of the soil specimen are not being truly horizontal, with the result plunger surface not being in full contact with the top of the specimen initially, and next, second, is that the top layer of the specimen being so or too soft or irregular. The CBR value can be calculated using the relation as CBR in percentage will be equals to the load or pressure sustained by the specimen at 2.5 or 5 mm penetration divided by the load or pressure sustained by the standard aggregates at the corresponding penetration level multiplied by 100. Now normally the CBR value at 2.5 mm penetration, which is higher than that at 5 mm, is reported as the CBR value of the material. However, if the CBR value obtained from the test at 5 mm penetration is higher than that at 2.5 mm, then the test is to be repeated for checking. If the check test again gives the similar results, then the higher value obtained at 5 mm penetration is then reported as the CBR value. The average CBR value of the three test specimens is reported to the first decimal place as the CBR value of the material, and if the variation in the CBR value between the three specimens is more than the prescribed limit, then the test it should be repeated on the additional three samples, and the average CBR value of the 6 specimens it should be accepted. As you know that the design curves correlating CBR is consists of the design curves correlating the CBR value with the total pavement thickness cover, which was developed by the California State Highway, the department, California State Highway Department, for the wheel loads of 3175 kg and 5443 kg, representing the light and the heavy traffic. Later, the design curve for 4082 kg wheel load was also obtained by interpolation for the medium traffics. Since it is possible to extend the CBR design curve for the various loading conditions using the expression as T equals to under root of P in the bracket 1.75 divided by the CBR value minus 1 upon P into phi bracket complete raised to 1 half, and second is T equals to 1.75 into P upon CBR into A upon pi bracket complete raised to 1 by half or 0.5. The expression will be applicable only when the CBR value is less than 12%. Here T is equals to the pavement thickness in centimeters, P is the wheel load in kg, the CBR is the California bearing ratio in percentage, P is the tire pressure in kg per centimeter square, and A is the area of contact in centimeter square. With this, we shall stop. Thank you.